In this program, we will review the procedures for rebuilding and reconditioning import blocks, rod and piston assemblies, and crankshafts. The program covers disassembly and cleaning procedures, shows how to measure components for wear, and determine whether parts can be reused, and covers machining operations and reassembly. Engine blocks are disassembled and reconditioned to correct problems such as oil consumption, engine noise, bearing failure, and damage caused by overheating or lack of oil. Some of the machining operations are typically performed in automotive machine shops that specialize in these procedures. The technician should be aware of all operations required to restore an engine to proper performance. Import engines, like most newer domestic engines, are metric. This takes some getting used to if your experience has been limited to older American-made engines. The dimensions of import and newer domestic engines are metric, and fasteners require metric wrenches. To help, most shop manuals give both American and metric dimensions and provide conversion charts. For engine work, you can quickly convert metric to inches by simply remembering that 1 millimeter is approximately 40 thousandths of an inch. This means that 0.25 millimeters is 10 thousandths, 0.50 millimeters is 20 thousandths, 0.75 is 30 thousandths, and so on. Follow the manufacturer's directions for block disassembly. Pay special attention to the placement and position of all engine accessories, hoses, wiring, and brackets. Make notes, use tags, sketch diagrams, or take photographs to guide you in reassembling the block later on. When removing the pistons and rods, be sure to mark the connecting rod and cap. This will enable you to match each rod to its respective cap and ensure that each rod and piston assembly is repositioned back in its original position in the block. A badly worn cylinder will have an unworn portion called a ring ridge just above the ring travel. This should be machined out using a ridge reamer before you remove the piston and rod assembly. Machining out the ring ridge aids disassembly and prevents possible damage to the pistons. Use protectors during rod and piston removal to prevent the connecting rod bolts from damaging the crankshaft. Mark the main caps to ensure correct placement for reassembly. And then remove the crankshaft from the block. During removal of the engine components, inspect all parts for any obvious damage or defects. Clean all reusable parts in appropriate cleaners. Cast iron blocks and cast iron or steel crankshafts should be cleaned in a hot alkaline jet cleaner. Aluminum parts, such as pistons or aluminum blocks, should be cleaned in a non-corrosive cleaner, such as a hot aluminum jet cleaner. Most other parts can be cleaned in a cold tank solvent. Carbon can be removed from piston heads by scraping using a groove cleaner for the grooves. Measure the parts after cleaning to determine if they are within specifications. Send repairable parts to a machine shop for machining and replace non-repairable parts with new ones. Begin by measuring the cylinder block and checking it for wear. The cylinder walls should be measured for taper and out of round. Follow the manufacturer's recommendations for wear limits. Typically, maximum taper is 0.2 millimeters and maximum out of round is 0.1 millimeter. Check the deck surface for flatness and compare it to the manufacturer's specifications. Cylinders within the manufacturer's specifications can be deglazed and prepared for reuse. If the cylinder is worn beyond specifications, it can be bored and honed to accept oversized pistons. Remember, always install and torque the main caps before machining the cylinder. Check the main housing bores for size and alignment. Torque the caps on the block. Then measure each housing for size and out of round and compare your measurements to the manufacturer's specifications. Measure the housing bores with a straight edge and feeler gauge to determine if they are aligned within the manufacturer's specifications. Blocks that are not within specification can be align honed or bored to correct the housing bores. Deck surfaces can be machined to correct any warpage. Check the crankshaft for cracks to determine if it can be reused. Magnetic particle inspection can be used to check for cracks. Use V-blocks to check the crankshaft for straightness. Refer to a bearing catalog or manual for the appropriate manufacturer specifications. Measure the crankshaft journals for size. If they meet specifications, they can be polished for reuse. Journals worn beyond specifications can be reground to a standard size of 0.25, 0.50, or 0.75 millimeters. Badly damaged or worn journals can be welded and reground to a standard size. Complete your check of the crankshaft by measuring the thrust surface dimension. Compare your measurement to the thrust surface dimension in the bearing manual to make sure that the end play will be correct. Remember, many undersized main bearing sets will have oversized thrust bearing surfaces. The crank will have to be ground accordingly. To determine if the pistons and connecting rods can be reused, check the rod bore for size and out of round. The rod caps should be torqued to the manufacturer's specifications. Then measure the rods for size and out of round to ensure that they meet the specifications in the bearing manual. Rods that do not meet the specifications can be reconditioned and reused. Pistons that are to be reused should have the ring grooves checked for wear. Use a new ring and a feeler gauge to check for side clearance. Measure the piston skirt diameter and compare it to the cylinder diameter for proper clearance. If new pistons are to be used, install them on the connecting rods in the appropriate sequence. The piston and rod assembly should also be checked for alignment before reuse. Prepare the block and other engine parts for reassembly by washing them with a strong detergent and water. Quickly dry and lubricate the newly machined parts to prevent rusting. New piston rings should be checked for size to match the cylinder size. Measure the end gap in the cylinder with a feeler gauge. Follow the guidelines in the information sheet that comes with the new rings. You should also refer to this information sheet as you install the new piston rings on the piston. Follow procedures and use tools recommended by the manufacturer. Install the main bearing halves in the block, noting the position of the thrust bearing and the oil hole locations. Lay the dry crank in the bearings and install the other bearing halves in the caps. Place Plastigauge across the journals so the clearance can be checked when the caps are torqued in place. Remove the caps after torquing to check for proper clearance. Lubricate the crank, bearing, and caps. Torque the caps in place. Then install the rear main oil seal. Check the end play of the crank by prying the crank forward and backward with a pry bar. As a final check, measure the turning torque of the crank. Lubricate the piston and rings. Install the piston and rod assemblies in the block using the proper ring compressor and bolt protectors on the rod bolts. Be certain rods and pistons are correctly oriented to the block and crankshaft. Plastigauge the rod bearings one at a time to check for proper clearance. Lubricate each rod bearing after checking the clearance and torque the cap and rod. Repeat this procedure on all rod and piston assemblies. Then recheck the torque on all rods and the main caps. Check the turning torque before installing the oil pan. This concludes the procedures on engine block rebuilding for import engines.
Piston rings may be quite simple in appearance, and replacing rings is not difficult for a skilled mechanic. So the extensive research and design that goes into making today's rings dependable and durable isn't obvious. But think of it this way. At 3,600 RPMs, these pistons hit top dead center 60 times each second, which means the rings change direction 120 times each second. And each time a ring changes direction, it exerts considerable force on the sides of the ring grooves. Finding ways to reduce this ring inertia force by reducing mass is a big challenge when designing smaller, more fuel-efficient engines. For every 1,000th of cylinder bore taper, a ring must open and close over 3,000ths at the gap. Even tiny tolerance changes can multiply into a great effect on ring performance. Yes, rings have some big jobs to do. And to do their jobs, they must work in an environment where all engine parts and support systems are in good operating condition. Of course, good sealing is the main job of the compression rings. On the firing stroke, the top ring should keep as much of the combustion gases above it as possible to assist in pushing the piston down. What gets by the top ring should be picked up by the second ring, because whatever gets past it to the crankcase is blow-by, which represents wasted power. The oil ring meters a controlled amount of oil to the cylinder wall to reduce friction, prevent scuffing, and help sealing, then returns the rest to the crankcase. The second compression ring also backs up the oil ring on oil control. If oil gets into the combustion chamber, it creates combustion problems, loss of power, and a smoking engine. Compression rings not only have to seal against the cylinder wall, they must prevent blow-by getting through between the ring and the piston groove. From its relaxed position on the intake stroke, the top ring is flattened by gas pressure against the bottom of the piston groove and pushed out against the cylinder wall. When it can't do this, it must be replaced. There are two critical ring wear areas, the face and the underside. As the piston moves up and down, rubbing action between the ring groove and the bottom surface of the ring gradually develops a wear step. Just a few 10,000ths will open a path for blow-by. Much of our ongoing piston ring research and development goes into minimizing the trade-offs between ring and cylinder wear, blow-by, oil control, friction, and cylinder wall finish, under the wide variety of conditions in which cars, trucks, tractors, and stationary engines must operate. Sealed Power is an engineering-oriented company on the leading edge of research and development for the engines we will be using in the future. It's a broad front of research focused on smaller, lighter engines with greater fuel economy. But to meet performance goals, tomorrow's engines must give higher horsepower per cubic inch, and this can only be achieved with higher RPMs, which puts heavier requirements on the rings. An important principle for top rings is the higher the RPMs, the lighter you want the ring to be, because the lighter the ring, the greater the RPMs before it becomes unstable and flutters. So the 5/64ths regular iron torsional twist top compression rings we have been using for years in most passenger car engines are slowly giving way to narrower, lighter compression rings. This is raising some challenging problems. The thinner the ring, the more careful the machining required for flatness. And cutting narrower piston grooves multiplies piston machining problems. Also, top rings must operate under higher temperatures and shock loads in the newer, lighter engines, so they must be made from high-strength materials to increase impact strength and high-temperature performance. As long as second compression rings operate at lower temperatures and shock loads, they will be made from regular iron. Because of our metallurgical research on heavy-duty and high-performance racing engines, we already have high-strength ductile iron rings in our line. The same impact force that will shatter a regular iron ring only bends a ductile iron ring. We're measuring the free gaps of these regular iron rings and these ductile iron rings for a temperature performance comparison. This sleeve represents the engine cylinder. And this furnace is set to the highest operating temperature of the top rings, 600 degrees. After 10 hours, the rings are removed. And after they have cooled, the free gaps are remeasured. The regular iron rings have heat set. The same ring before, the same ring after. The ductile iron rings are still the same dimension. The same ring before, the same ring after. Most top rings are now faced with molybdenum. Moly's higher melting point and oil carrying capacity gives better resistance to scuffing than plain iron or chrome. Under a microscope, you can see the surface voids which carry lubrication and provide a place for wear particles to go. Electroplated chrome facings are used for most tractor and heavy-duty top rings. Chrome is harder and has less porosity than plain iron or moly, so it wears well and stands up better under dusty or dirty conditions. Of course, dirt is the enemy of cylinders and rings. A normal fuel mix is 10,000 to 1, which is a lot of air for 1 gallon of fuel. It is said that if you have a 1/16 inch diameter leak anywhere in the air intake system, you just as well not bother installing an air filter. All top ring faces are lapped at the factory. They are rotated and reciprocated in a cylinder the same diameter as those they will be run in, then polished to make them seat and break in quickly. There is a growing use of LPG and natural gas in stationary and fleet truck engines. Because these are cleaner burning fuels, chrome-faced compression rings are not recommended. For most LPG engines, we recommend our sets which have a plain iron top ring. For heavily loaded engines, moly-filled rings may be used when converting to LPG. Moly rings that are already mated need not be changed. The trend to smaller diesel engines is presenting ring design challenges. Soot and deposits from the burning of diesel fuel have always made sticking and wear a problem. Currently, heavy-duty keystone ring designs are being tested and adapted to downsized diesels. For all the technology and research that goes into our rings, we still depend on the mechanic who services the engine. Let's cover some engine servicing tips. When an engine's using too much oil, you'll only know it's an internal problem after you've checked rocker cover and pan gaskets, seals, and the drain plug for leaks, also the PCV system. With the heads off, look for oily deposits in the intake ports or on the underside of the valve heads. Oil loss also can occur past the exhaust valves. Leakage develops from valve and guide wear. Your jobber's machine shop can take care of this. Of course, whether you find signs of leakage or not, there is no question about sending the heads out anyway, at least to have the valves ground and to replace the old valve stem seals, or to have the valve guides machine to accept our positive type valve stem seals. These seals were developed by Sealed Power after our research proved the tremendous importance of good stem-to-guide sealing in today's engines. The 3 valve guides on the right do not have valve stem seals. We are installing seals on the other 3 guides. We can compare oil leakage by means of this laboratory valve test fixture. With a vacuum applied to the crankcase, the jars below collect any oil sucked down between the valve stems and guides. After several hours, we can see why, if this engine were running at 50 miles per hour on a vehicle, leakage would be 1 quart of oil every 350 miles without seals, but only 1 quart in 14,000 miles with valve stem seals. When we put an engine without seals, but with stem-to-guide clearance well within factory specs through our standard oil consumption test routine, it used 1 quart of oil every 500 miles. But see what happened to oil consumption on the same engine when we added our valve stem seals. We know they do the job. If the decision is made that oil consumption is an internal problem requiring piston removal, any carbon or wear ridge should be removed. Failure to do so may damage the piston lands. Don't machine any deeper than necessary to remove the ridge because you could spoil the ring contact surface below, which could lead to blow-by or ring breakage. After the pistons are removed, the cylinder bores should be checked for taper and out of roundness with a dial bore gauge. On most engines, the bores are not likely to be out of the manufacturer's wear limits. But you certainly will find glaze. You can forget your glaze breaker because it isn't a problem if you're going to re-ring with our precision-finished, pre-seated rings. They're designed to seat on glazed cylinders. You may find scuffs or scratches. These should be removed by light, wet honing. Be sure to use a rigid hone with the proper grit size and drill speed. Use a reciprocating movement, which will give you a crosshatch finish 20 to 30 degrees off the horizontal surface of the block. Wet honing will cut cleaner and faster than dry honing. If the cylinders are beyond the manufacturer's wear limits, the bores must be resized for oversized pistons. We recommend boring or rough honing to 2 or 3 thousandths under the finished size. Here's why. When a cross-section slice taken from a rebored cylinder wall is highly magnified on our research microscope, we can see fragmented material and the horizontal boring tool marks, which must be removed by honing. Here is another view of a typical thread finish from boring, highly magnified. If not honed, the rings would have to try and make their own bearing surface. Failure to get below the thread finish, or using too coarse a stone, allows the cylinder to retain excess oil in the crevices which the ring cannot reach. This will create an oil control problem, or the conclusion that the rings didn't seat. Both the rings and the bore must seat. A narrow, precision-finished ring face cannot process 3 inches of an inadequately prepared cylinder surface. The rings will seat, but the bores will not. It doesn't take much oil to create an oil control problem. 1/10 of a drop of oil per explosion in a 6-cylinder engine turning 3,000 RPMs, about 60 miles per hour, would consume 1 quart of oil every 40 miles. A big cause of ring failure is underrating the importance of thorough cleanup after honing. Do not use gasoline or solvent. Use hot water, soap, a brush, and the patience to make certain there are no abrasive metal particles anywhere inside that engine. Dry with paper towels. Any discoloration on a towel means you should go in and scrub again. Be sure the bores are completely dry before you oil them. Bearing clearances are also important to oil control because the oil must get through that clearance to the cylinder walls, rings, and pistons. Half the manufacturer's clearance reduces oil throw-off 5 times, insufficient for lubrication. Twice the recommended clearance increases oil throw-off 5 times, far more than the rings are designed to control. It makes sense to mic the crankshaft journals for proper diameter and roundness to determine whether you can replace with standard bearings or if you'll need undersized bearings. When you're removing the old compression rings, use this tool. If you break them off, you run the risk of scratching or gouging the ring grooves. If you find any carbon in the ring grooves, use this safe, inexpensive groove cleaning tool. After you've cleaned out the carbon, it's 100 to 1 you'll find the grooves are okay. But check the new rings for side clearance just to make sure. Normal clearance is 2 to 4 thousandths. It should never be more than 6 thousandths. Ring grooves are more than just slots which hold the rings on. The arrows show the sealing points for the top ring and the second compression ring. These rings can form a good seal only against groove surfaces which are true and flat. So if you find worn top grooves that can be repaired with GI 60 inserts, send the pistons to your machine shop. It's the simple things which should be checked most carefully. If you install the compression rings upside down or in the wrong grooves, you can turn an otherwise good job into a disaster. The instructions which come with the new rings should be read carefully. And the marks on the rings are there to help you install them right side up. This dependable oil ring is used by every major car manufacturer. The electro-polished stainless steel expander spacer has the best corrosion resistance of any ring ever made. It exerts uniform outward pressure through a number of spring tension points on the two steel rails. The expander's solid box-like design completely supports the rails at the front and back of the groove. The rails have chrome-plated wear surfaces, which are factory preseated. Dozens of spring tension points apply constant pressure against the cylinder walls. Over 1 billion of these SS50 oil rings have been installed. To make sure you have the right size compression rings, push a new ring down to the lower unworn area and measure the gap. Three to 5 thousandths per inch of bore diameter is normal. However, in used cylinders, the gap may go as high as 30 thousandths. Using a ring expander rather than your thumbs is the best way to avoid overstressing a compression ring, which may cause it to fracture after the engine is back in operation. Rod bolts can scratch or cut if not covered. Before you put the piston back in, make absolutely sure you're putting the right rod and piston back into the right cylinder, in the right direction. Of course, you'll use a ring compressor, because this is the best tool for simple installation. Make sure it's flat and square to the top of the block. The piston should move down fairly easily. If you have to force it in, don't. It means something is wrong, usually a ring which hasn't been properly installed on the piston. As our engine design experts work on tomorrow, the shape of the future is clear. The internal combustion engine, as we know it today, will be with us for a long time to come. And no matter what is engineered into new engines, careful, thorough, knowledgeable service work will continue to be essential. So, from one group of engine experts to another, you, the engine service experts, we all share a promising future.
The world's largest manufacturer of piston rings presents some suggestions for finding what needs repair or replacement when reconditioning passenger car engines. Let's assume the engine's using too much oil after 70,000 miles or so. And by now you know it's an internal problem because you've checked external lines, gaskets, seals, and the drain plug for leaks. You've also found that the PCV system's okay. As you remove the push rods, don't forget to tag them by location and direction. They may differ in length, and you can avoid adjustment problems later by putting them back in the same order. With the heads off, the first thing to look for is oily deposits in the intake ports. On overhead valve engines, oil loss also can occur past the exhaust valves. Leakage develops from valve guide wear, and your jobber's machine shop can take care of this when they refinish the heads. Of course, whether you find signs of leakage or not, there's no question about sending the heads out anyway, at least to have the valves ground, and to replace the old valve stem seals. Just as with gaskets, any rubber or composition parts should always be replaced. Whether you find a ridge or not tells you a lot about the condition of the engine. Ridge is caused by cylinder wear where the top ring stops. If you find ridges, they must be cut with a ridge reamer before you can remove the pistons, so you won't risk damaging the piston lands. After the pistons are removed, the cylinder bores should all be checked carefully with a dial bore gauge. Make two measurements perpendicular to the crankshaft, one near the top, the other near the bottom of the ring travel. Write the measurements down. Next, make these measurements parallel to the crank. If the taper exceeds the manufacturer's tolerance or out of roundness exceeds 3/1000ths, the block should be rebored. Your jobber's machine shop can take care of this for you. When you check the bearings and they're badly worn, it also means that you should check the crankshaft for wear. If the bearings are not worn appreciably, it still makes sense to mic the crankshaft journals for proper diameter and out of roundness to determine whether you can replace with standard bearings or you'll need undersize bearings, or if the crank should be sent out for regrinding. As you check the pistons, a wear pattern such as this means that the connecting rod needs alignment. A simple task for your jobber machine shop. When you're removing the old compression rings, use this tool. If you break them off, you run the risk of scratching or gouging the ring grooves. The importance of the side surfaces of the ring grooves to sealing should always be regarded. The sides of the ring grooves must be true and flat for piston rings to form a good seal. Gouges, scrapes, or too much wear can cause loss of compression or oil leakage. So respect those groove surfaces when you're cleaning the pistons. If you do find carbon, use this safe, inexpensive groove cleaning tool. Use a scraper to clean the tops of your pistons. With most engines, you'll find that sending the heads to your jobber machine shop will take care of everything you don't have tools to handle. And if you run into any special problems, reboring, warpage, excessive wear, your jobber can back you up and help you provide problem-solving, dependable engine service.
Seal Power and American Hammered present some recommendations on oil pump replacement. When that oil light comes on, you're jumping to conclusions if you immediately say the car needs a new oil pump. Maybe so, maybe no. That light does indicate there's something wrong with the oil system and that the engine could be running on the edge of catastrophic failure for any one of a number of reasons. In this time of self-service gas stations, many people don't check their oil, and some engines have been known to have the wrong dipsticks. The oil pressure sending unit may not be functioning properly, thereby giving a false reading. If the test gauge shows normal pressure, according to the OE specs for the car, you know the problem is in the sending unit or related wiring. But if your test gauge confirms the low pressure situation, you should drop the pan and check the oil system with a bearing leak detector attached at the sending unit opening. With the system pressurized, you can check the bearings for runoff. 60 drops per minute is considered average. If the drip rate is okay, the bearing should be okay. A large or steady stream indicates wear and the need for replacement. Before condemning a bearing, rotate the crankshaft to half revolution and check again. If you find excessive runoff, just replacing the pump may raise the pressure enough to put the light out, but the wear will still be present, and down the road, when the engine wipes out, your customer may blame the new pump and you. If all main, rod, and cam bearings indicate normal oil runoff, replacing the pump may take care of the low-pressure problem. But first, check the bottom of the oil pan. Foreign particles indicate worn or damaged engine parts, or a previous sloppy repair job. This debris can damage or destroy the oil pump. There are 3 different oil pump designs in common use. All are positive displacement pumps that should last for the life of the engine, if properly installed, if not forced to operate in a highly contaminated environment, and if not the victims of other part failures. The oil pump must provide adequate pressure and volume to move the oil through the lubrication system. Most engines have what is called a full flow filtration system. Oil from the crankcase is picked up through a filter screen. The faster the pump turns, the greater the volume and pressure. So a pressure regulating valve designed to open at the maximum desirable pressure allows some oil to bleed off and return to the crankcase. The pressurized oil goes through the oil filter, and the filtered oil is sent through gallery openings in the engine block to the moving engine parts. From these, the oil drips back into the pan. When you consider that an engine with about 5 quarts oil capacity may pump as much as 30 quarts a minute through the lubrication system, you can realize how rapid and constant this oil flow must be. Adequate pressure is needed to force oil to the moving parts with sufficient volume to ensure a flow of lubricant throughout the entire engine. Both are dramatically affected by the amount of runoff from the clearances between engine parts. That is why excessive bearing clearance can increase the flow beyond the capacity of the pump and cause pressure to drop. The filtration system is designed with circulating oil as its first priority and filtering as its second priority. If flow through the filter becomes restricted, a relief valve in the filter or filter housing opens, allowing unfiltered oil to bypass directly to the engine galleries. Unfiltered oil makes engines susceptible to premature failure through foreign material entering close tolerance areas. So it's imperative that oil filters be clean and unrestricted for maximum protection. The pickup screen also has a bypass valve. The bypass valve opening usually seals against the surface of a metal shroud or cross strap. But on cold starts, when the oil is too thick to pass easily through the screen, or at high engine RPMs when the pump is circulating maximum volume, the bypass may open. And of course, if the screen is plugged, the bypass will stay open whenever the engine is running. As oil rushes through the bypass valve, a vortex may be created in the oil pan. The vortex can pick up debris, either in suspension in the oil or lying on the bottom of the pan, and pull it into the pump. Even though the pump lives in oil and is as resistant to wear as any part in the engine, dirt or debris getting through the bypass can cause trouble. For those who find it hard to believe that large particles can get past the pickup screen into the pump, witness our collection of horror stories. This pump locked up because it picked up a snap ring, which was forced from a hydraulic lifter due to excessive valve lash. Of course, when a pump seizes, the intermediate or drive shaft is twisted off or sheared. A piece of an aging valve stem seal took care of this pump. A check on the valve stem seals revealed that they all were deteriorating. The pump was the victim, not the cause. This pump points the finger at the guy who replaced the rocker cover gaskets, then flunked on thorough cleanup. Scraped gasket material got into the pan and was sucked into the pump. A small piece of wire from a brush jammed between the rotors of this pump and caused seizure. You can be sure that if the intermediate shaft or the drive slot in the pump shaft is broken, debris caused the pump to lock up at least momentarily. Such seizures can also strip the gear at the camshaft or distributor oil pump drive. Nylon from timing sprockets can break loose and jam the rotors. Scoring or deep scratches prove that abrasives were circulating in the engine oil, probably because the oil and filter were not changed at proper intervals. Or it could mean that abrasives were entering the engine through the air intake or crankcase ventilation systems. This replacement pump didn't last long because the installer, when attaching the pickup screen, clamped the pump body in his vise rather than clamping the shaft housing area. How do we know this? He distorted the housing, causing interference between the inside surface and the rotor. Another replacement goof. The installer cut slots with a hacksaw to make it easier to attach the pickup screen, probably in an effort to salvage an old screen. His modification caused an air leak. An air leak on the suction side of the pump allows air bubbles to enter the system. Air bubbles can cause aeration of the oil, leading to foaming, marginal lubrication, hydraulic lifter noise, and parts failure. This kind of leakage can be caused by trying to weld or braze a loose fit. We are trying to prove several things with this horror collection. First, that oil pump failures are rarely the fault of the pump itself. Second, that examining the inside of the old pump will usually give you clues to what actually caused the failure. Also, examination of the oil pan. Debris often tells its own story. Third, don't put on a new pump without correcting other problems. It should be a matter of good sense and professional pride to protect your customer's investment in the new pump. You are also capitalizing on the most mutually beneficial opportunity for additional profitable service work. Failing to make necessary repairs is sending the cart down the road to an inevitable wipeout of your good work, blame from your customer, and probable loss of service business to a competitor. After you have corrected any possible cause of pump failure, you can install our replacement oil pumps with complete confidence. Each pump is thoroughly inspected and tested for volume and pressure before leaving the factory to specifications at least equal to the original equipment standards for those which they are designed to replace. We recommend installing a new screen with the new pump, and use the proper tool to get a good press fit without squeezing, bending, or rough handling. It's all right to use Loctite or epoxy. Brazing or welding is not recommended. Prime the pump. Turn the shaft and make sure that all internal surfaces are covered with oil. When installing the pump, it's important that the intermediate shaft is properly engaged. You can crack some pumps that fit into recesses if they're not properly positioned. One hand should hold the pump steady, while the other puts in the bolts finger tight. On engines where there is a possibility of crankshaft interference, check the clearance before torquing. The bolts should be torqued to the engine manufacturer's specification. After filling the crankcase, but before starting the engine, use your pressure tank to prime the oil system. Remember, oil pumps are usually the victims rather than the cause of oil system problems. Good engine service requires pinpointing and eliminating the true cause of pump failure.